Hocam,
All right, welcome back. So do you have any questions?
hocam başlamadan hemen sorabilir miyim?
Yes, please.
Emin olmak için soruyorum da eğer
Tabii tabii.
B1'dan B2'ya dönüşüm yapsaydık B1'ın vektörlerini yani V1,
Exactly. Suppose
B2'yi
if we
B1,
were
B3 şeklinde
given
yazacaktık.
A3, which were, let's say, B1 to B2, okay? So we will first pick those guys, right? And I was going to express AV1 in terms of V1 and V3, okay? So it will be equal to something V1 plus some other coefficient times V3. And AV2 I was going to express V1 and V3.
Teşekkür ederim.
Perfect. Any other questions? Şuraya da şey yazayım bari, coefficient yazayım. Alpha 1, alpha 2, beta 1, beta 2, and A3 will be alpha 1, alpha 2, beta 1, beta 2 there. Okay. So let's continue with another example then. All right, so now we are given the vector space of 2 by 2 real matrices, and the linear mapping is given as A of V is equal to SV times V times S transpose, where S is equal to this S01 minus 10 matrix, okay? And then when we are given two basis sets which are equal, so both B and B bar are equal to each other, and it's a canonical basis over here as far as I can see. And we would like to find the matrix representation of that linear transformation over here. So to investigate that, maybe let's see what if we are given a 2 by 2 real matrix, okay? Let's say V is equal to A, B, C, D, both all real numbers, these A, B, C, D's are. Let's see what is the real linear transformation of that matrix over there, okay? So let's try to write down AV and see what happens to that. Because later on I will replace those V's with the basis vectors in B over there, but I would like to first see what happens to this general ABCD vector over there. Okay. So it says that it's S times B is given as 0, 1, minus 0, 1, minus 1, 0 times A, B, C, D plus V itself A, B, C, D times A, B, C, D times S transpose, right? So it is 0, minus 1, 1, 0 over here. And that will be equal to what? So this will be equal to C and then D, and that will be equal to minus A and then minus B, the first term over here, and the second term is equal to what? B over here and minus A, and that will be D over here and minus C, right? And the summation of these two by two matrices is equal to what? B plus C, D minus A, was it minus A over here? Then D minus A once again, D minus A and minus B minus C. Minus B minus C. So if I was given this ABCD matrix, this linear transformation becomes B plus C, D minus A, D minus A, minus B minus A, right? By the way, what is the representation of this V vector with respect to basis B? So what is the representation of this V vector with respect to basis B? If it is A, B, C, D, it is A times the E1, like if these are called, let's say E1, E2, E3, and E4, it's A times E1, B times E2, C times E3, and D times E4 is V, right? And I will write down those coefficients in vector form, so it will be equal to A, B, C, D then, right? How about the representation of the linear transformation with respect to basis set B? So what is representation of A with respect to B bar over here, which is equal to B? That will be equal to what? B plus C, D minus A, again D minus A, and minus B minus C. Okay. And we are looking for the linear transformation matrix such that this ABCD times a matrix A gives me that linear transformation. Sorry. So what I'm looking for this right? So B plus C, D minus A, and minus B minus C is equal to what a matrix A times this representation of the original vector respect the basis B, B, C, D. And I'm looking for this matrix over here. So in order to do that, if we follow the procedure simply, what should we do? I should pick the vectors in my domain first, these E1, E2, E3, and I should write down their linear transformation in terms of the basis vectors in B bar, which was again B. Okay, so I will compute the linear transformation of these vectors and express them in terms of these basis vectors over here. So let's have a look at first linear transformation of E1. Okay, so notice that E1 matrix is the case where we have A is equal to 1, B, C, and D is equal to 0, right? So let me write down as maybe on top of here to be more explicit. So for E1, A is equal to 1, and all other coefficients are equal to 0, right? And in that case, what is A of E1? So we found A of any vector over here for A, B, C, D, right? So anyways, so A is equal to 1, all other coefficients are 0 for E1. So A E1 will be equal to, I will express that in terms of, let's say, E1, what's happening? 1 second, please. Okay. I will compute AE1 and express it in terms of E1, E2, E3, and E4, right? That's what I will do. And as you see over here, so what is the coefficient of AE1? What is the coefficient of E1 if I would like to express A of E1? So that corresponds to the case A is equal to 1, B, C, D are all equal to 0, right? So the first coefficient, the coefficient of the first vector is B plus C. Both of them are equal to 0, so that will be simply equal to 0 over there. So what is the coefficient of E2 over here? So I'm talking about this coefficient when A is equal to 1, D is equal to 0, that is equal to minus 1. And what is the coefficient of E3? So it is equal to D minus A. So D is equal to 0, A is equal to 1. It's again minus 1. And what is the coefficient of E4? So when B and C are equal to 0, that is equal to 0. Okay. And the next thing, I will write down A, E2 in terms of E1, E2, E3, and E3. Okay. Plus E3 plus E4. Okay. And for E2, I can write it over here. And for E2, it is this matrix over there. So A is equal to 0, B is equal to 1, C is equal to 0, D is equal to 0. Okay, so we're simply saying that B is equal to 1 and A, C, D are all equal to 0 for E2. And so given a ABCD, this linear transformation was given as this matrix over there. Maybe I can show that thing more explicitly. So what is this matrix equals to when B is equal to 1 and all other coefficients are 0? So the coefficient of E1, then it will be simply equal to 1. And the coefficient of E2 is going to be that element over here, which is D minus N, which is equal to 0. And again, this coefficient is the same as the previous one, so it is equal to 0. And that coefficient, that will appear as the coefficient of E4 over here, is equal to -1 when B is equal to 1 and C is equal to 0. And if I continue that way, let's write down A of E3. And E3, we're going to have C is going to be, so let me show you once again. E3 is this matrix over here. So C is equal to 1, all other coefficients are equal to 0. So if I write down then the transformation of E3 as a linear combination of E1, E2, E3, and E4, the coefficient will look like something like this. Let me write down the vectors first so that I can write down the coefficients in red color. Okay, so C is equal to 1 this time, the all coefficients are equal to 0. So then it will say that the first coefficient will be equal to 1 over there. These coefficients are going to be 0, D minus A are equal to 0, and this is equal to -1. And lastly, if I write down the linear transformation of E4, which corresponds to D equals to 1, all coefficients are equal to 0, and I should be writing the linear transformation of that vector, which is this matrix over here, when D is equal to 1, all coefficients are 0, as 0, 1, 1, 0, right? So it will be something like this, 0, 1, 1, 0. Then what is the next step in our procedure? I will write down these coefficients as the columns of the A matrix, okay? So from there, let's say the A matrix will be simply, the first column will be equal to 0, -1, -1, 0. The second column will be 1, 0, 0, -1. Third column will be 1, 0, 0, -1. And the last column will be 0, 1, 1, 0. And also, you can verify that if you replace this, maybe I can put it explicitly. So if you replace this A matrix over here, I couldn't plot, but maybe you got it anyhow. As you see, for example, what is the first row of this A matrix? 0, 1, 1, 0 times ABCD is equal to B plus C, right? And as you see over here again, if you multiply the second row with ABCD, then you obtain D minus A. Again, D minus N, A. And for the last row, if you multiply 0, -1, -1, 0 with ABCD, you will get minus B minus C, okay? So we were able to obtain the A matrix correctly. You can verify that as well. Şuraya da ok koyalım madem. Do you have any questions? So we followed exactly the same procedure, right? So we write down AE1 in terms of the basis vectors, AE2 in terms of the basis vectors. But since that was a complicated linear transformation, so we first tried to write down a general expression for the linear transformation of matrix given as ABCD. I obtained this matrix, and I just write down the coefficients of entries of these bases over here, and obtained those coefficients. Do you have any questions? Is there anything I can explain better there? If not, let's continue with another example. Okay. All right, so in our next example, the v is given as the function, some real functions getting real values, and f is a polynomial with degree less than or equal to 3. Okay, and a linear transformation A is defined from V to V, so from domain to codomain, and A of f is equal to the derivative of f. All right. And choose the basis set to be B as 1 as S square S cube, and find the matrix representation A with respect to basis B both in the domain and the codomain. Okay. So once again, if we are asked a matrix representation of a linear transformation, first question is what are the bases in the domain and codomain. In this case, they are the same. All right. And so what we will do is that, so suppose we are given, a vector v in our domain V, okay? So such that v is equal to, let's say, f of s. And since that's a polynomial with degree less than or 3, I can express this polynomial as a plus bs plus cs square plus d s cube for some coefficients a, b, c, d there, right? And if that polynomial can be expressed as a linear combination of these vectors as follows, what is the representation of this polynomial with respect to basis b? What is the representation of v vector with respect to basis b? It's those coefficients, right? A, B, C, D is over here. So A, B, C, and D. So it's going to be 4x1 matrix. All right. So what is the linear transformation of F? So let's say A of F is equal to D over ds F of S. Okay. And that will be simply equal to B plus 2c s plus 3d s square. So then what is the linear representation of AV with respect to basis B? So I can write down as 0 times s cube as well. And I write down these coefficients in a 4x1 vector, right? So it will be B, 2c, 3d, and 0. Okay, and what I'm looking for is basically, I would like to find that representation vector over here as a matrix A times, okay, I'll call this guy as A, times the representation of my original vector V with respect to B, okay, so it is A, B, C, D, A, B, C, D over here. Okay. So notice that I can fill in this A matrix rows as follows. So for example, for the first row times ABCD should be equal to B, right? So the first row is equal to 0, 1, 0, 0, right? The second row times ABCD should be equal to 2C. So it should be 0, 0, 2, 0. And the third row is going to be ABCD times that third row should be equal to 3D. So it will be 0, 0, 0, 3. And the last row is going to give me a 0 for whatever ABCD I have. So I will have 0, 0, 0 over there. So I can obtain the A matrix in this form as well. Okay, so that was another way of doing that. And notice that that thing is still same as, maybe I can pick another color over here. So notice that A is still, if I can write, sorry, is the same matrix that we were talking about. That if I call these vectors as E1, E2, E3, E4, that is equal to the representation of AE1 with respect to the basis B, okay, the first column, so like this, and the representation of AE2 with respect to B2. So what is the linear transformation of AE1? So it is derivative of 1, right? And the derivative of 1 is a constant is equal to 0. And the representation of the 0 polynomial is equal to the all vector 0, 0, 0, 0 vector over here, right? That's the first column. And what is the linear transformation, the derivative of S, E2 over here? That is equal to 1, right? And the representation of one polynomial with respect to this basis is equal to 1, 0, 0, 0, okay? And if you continue like that, the third column is going to be the representation of A, E3 with respect to B3. And the last column is going to be, I couldn't write, but representation of A, E4 with respect to B. Okay. Sorry for bad writing, but if you write a slide to the left, it will be better. So this was the original procedure to find out these basis vectors. This representation matrix representation of linear transformation. And here we showed another method, right? By just studying the representations themselves, we can also find this A matrix. They are the same. Do you have any questions here? Anything I can explain better? If not, next we will try to the effect of changing bases in the domain or codomain and on the matrix representation of the linear transformation. Okay, so that's the next thing we will do. So let's try to do that together. Okay. So given the matrix representation of a linear transformation A with respect to basis sets B and C, and one can draw the following diagram considering a change of basis. Okay, so in the case that suppose you change the basis set on your domain to B bar, and suppose you change the basis set into another basis set as in your codomain as another basis set C bar, then what is the relationship between A and A bar? So I will try to write that down as follows. So let's start from a vector V over here in our domain, okay? And that V vector, if I pass through a linear transformation A over here, suppose I obtain the W vector over here, okay? All right, and I'm given two bases sets. One of them is in my domain B, and one of them is in the codomain C. So I can express the representation of that vector with respect to B over here. So suppose I do have this, which is the representation of vector V with respect to basis B over there, okay? And I can also express this W vector as a linear combination of vectors in basis C. So I can write down also the representation of this W vector with respect to basis set C over here, okay? And between those two, I can define the matrix representation, right? So then I can, between those two representations, I can get a matrix such that representation of W with respect to C is equal to A times representation of V with respect to B over here. Okay, so the next thing that we'll investigate is that suppose I change the basis set in the domain from B to B bar. Okay, so let me get that blue color. Suppose I do have, I change the basis set in my domain to B bar and obtained the representation of that V vector with respect to the new basis set B bar, right? So notice that there's also a relation between the representation of a single vector with respect to two different basis sets. We know that there was a invertible matrix that defines that relationship, right? So I can convert one representation into another by defining a invertible matrix. So as you might remember, I can say that representation of VB can be written as a P matrix times representation of V with respect to V bar. Okay, so I will show that with that P matrix over there. Okay, and once again, suppose that I changed the basis set in my codomain into C bar. So I will write that thing as C bar. And again, once again, suppose there's a transformation between those representation by using an invertible matrix, let's say Q, such that representation of W with respect to C bar is equal to Q times representation of W with respect to C. Okay, so this is what we have done before when we were changing the basis for representing a single vector, right? And so if we go back to our linear transformation, the relation between W and V, so W was equal to A of V, we can obtain one matrix representation with respect to basis sets B and C, and we can obtain another representation of the same linear transformation with respect to basis vectors B bar and C bar. So I will show that with that line over here. So this is a second matrix, let's say A bar, and that A bar combines the representation of W with respect to C bar to representation of V with respect to B bar over here. And our question is, what is the relationship between A bar and A? All right, to find out the A bar matrix, the relation between A bar and A, I will start from writing down the representation of W with respect to C bar. So let me pick a pen first. So I can start from expressing the C representation of W with respect to C bar as Q times representation of W with respect to C, right? And we also know that the A matrix defines the relation between the representation of W vector in C and the representation of V vector in B, right? So I can write that thing as Q times A times representation of V with respect to B, okay, from this equation over there. And lastly, I can write down the representation of V vector with respect to B as a invertible matrix P times the representation of V vector with respect to B bar over here. So I can write that over here, write that as Q times A times, instead of this term over here, I will write P times V with respect to B bar over here. So I managed to obtain an expression for which relates the representation of W with respect to C bar to the representation of V with respect to B bar, and that the intermediate matrix over here is actually equal to A bar matrix, right? So A bar is equal to Q times A times P. So this might be useful in the cases, for example, and without the first, I think the most useful part is this. If I know a linear matrix representation of a linear transformation with respect to given bases B and C, and if I know the matrices that converse representations of B to B bar and representations of C to C bar, I can find the matrix representation of the linear transformation with these new basis sets B bar and C bar without even knowing the linear transformation itself, right? So I can simply study this A matrix, Q matrix, and P matrix and find A bar. Remember that previously, in order to find the linear transformation, the matrix representation of a linear transformation, we were studying the linear transformation of the basis sets, and we were trying to express the linear transformation of every single basis set and express them in terms of the basis sets in our codomain. Without all these hustles, by just inspecting those Q, A, and P matrices, I can write down the matrix representation of linear transformation with respect to new basis sets, B bar and C bar. So that might be handy in many situations. And furthermore, that's also some part of the motivation. While towards the end of the course, we will skip dealing with these linear transformation themselves, but we will be dealing with their matrix representations instead. So we will leave this calligraphics A's behind and work with their matrix representation. Okay. And do you have any questions here? I can maybe explain a little bit further. Okay. Okay, and there's one special case here. Let me try to illustrate that thing as well. So I was talking about the functions V in a domain, right? So this was my domain was V and my codomain was somehow W. And in many cases, you are getting the vector V over here and you compute linear transformation of AV, and that is mapped again in another different vector space, but it is mapped back into the same vector space. So back to V as well. So maybe I can try to plot that more explicitly. So if I get V vector, and if I, let's say, get the AV over here and get to this W vector over here, which is again in our codomain, since the domain and codomain are chosen to be the same. And then if I change the basis set, so I will have the representation of that vector with respect to B over here, okay? And I can get their linear transformation and get that thing as the A matrix over here, and I can get the representation of the same vector V over here, and defined as in terms of B bar, and I can get the linear transformation of that guy and map it back to to my domain and obtain a matrix representation A bar over here. Then I can write down the new matrix representation A bar as P inverse AP. Okay. So in that pitch, it was like if B and C are the same, and if B bar and C bar are the same, then this Q is equal to P inverse, okay? So if B is equal to C and B bar is equal to C bar, I'm simply saying that, then Q is equal to P inverse, okay? And if you write Q inverse in this equation, that A bar is going to be simply equal to P inverse times AP. Okay, so the last example is, maybe you can do it first. You can first try yourself, and maybe we can start the next lecture with this example. So we go back to the very same example where we find two different matrix representation. So suppose we found this A1 and A2 matrices as before, and let's try to find those A1 and A2 in terms of each other by applying this A bar is equal to QAP approach, okay, by applying the change of basis approach that we have considered here. So maybe you can first try that yourself, and then we can start the next lecture from this example. Following that, we will continue with one of the most important theorems. So it is the rank nullity theorem. Maybe I can write down the name as well. Theorem. So we will continue with the proof of the rank nullity theorem right after this example in our next lecture. Well, but I will see you on the quiz tomorrow, right? So we will meet at 7 tomorrow for our quiz. So I'm looking forward to see you there. Hope everything goes well this time.